Welcome, scholars, to Mr. Honeycutt's math class. We are looking at the shapes of functions, why they have the shapes that they do. On this video, we're going to look at exponentials and logarithmic functions, the inverse of exponentials. So we're going to start here with an exponential function 2 to the x. We're using 2 and 3 and not e because it's much easier to work with by hand. Okay. So 2, just walking through this right now, this is so f of the input is equal to 2 to that input, and 2 to the negative 3 is equivalent to 1 over 2/3, which is equivalent to 1/8, which is going to be a small value. So plotting that point, it's going to be, I'm over here at negative 3, and then somewhere around like an 1/8 or so. All right, so it's going to be somewhere right about there. Okay. 2 to the negative 2 is going to be 1 over 2 squared, which is 1 over 4. Okay. Plotting that value, it's going to be, so that's 2 to the negative 1 is going to be 1 over 2 to the first, which is just 1/2. So over here at negative 1 is going to look right about there. 2 to the 0. Notice that over here, let's say you completely forgot your negative rules, but notice the pattern here, we're just doubling each time. Okay? So what this means is that, in a sense, it's like 2 divided by 2, which is just going to be 1. Okay? So at the 0, it has a point of 1 and a y-intercept of 1. 2 to the first is just 2. Just 2 to the first, which is just 2. So at the first pattern, there it is. 2 squared is just 2 squared. So that's 4. So at that, it's going to be that. And then 2 to the third is just 8. Graphing this, we can see it has the shape of an exponential function. So that's the basic shape that it has. Notice when I taught Algebra 1, I called it like an airplane taking off shape, I guess. It's kind of a way to think about it. So notice the domain is all reals. We have a value for all of this. Notice the range is from 0 to positive infinity. I want you to note this right here. It never actually gets to 0 except at the left end. Okay, the limit as this goes to negative infinity would be 0, but it does not have the bracket here, which is different from, say, an x to the even, which does have that closed bracket because it touches 0. This one doesn't until it gets to infinity. So the left-end behavior is actually 0, all right, and the right-end behavior is positive infinity. It is increasing for all reals, and it doesn't have decreasing maxima or minima. I'll look at the 3 to the x, and you'll see that it's very, very similar. So I've got 3 to the negative 3. That's going to be 1 over 3 cubed. That's going to be 1 over 27. So that's going to be like maybe right there. I have 3 to the negative 2. That's 1 over 3 squared, which is 1 over 9. 3 to the negative 1. That's going to be 1 over 3 to the first, which is 1/3. 3 to the 0 is kind of like 3 divided by 3, which is 1. Okay. 3 to the first is just like 3 to the first, which is just like 3, so that point's going to go right there. 3 squared is just like 3 squared, which is 9. That's what it is. So notice it's actually a little bit, if you can kind of see, it's a little bit steeper than this one is. And that actually, the base will change how steep the exponential is. The domain is also all reals. The range is 0 to infinity. The left-end behavior is 0. The right-end behavior is this. And it is increasing for all reals. So notice the difference between this one and this. What's the difference between this and the x squared, which has that u shape, and this and the x cubed, which has, well, it's not drawing that for some reason, but it has this shape. Okay? And the difference, I hope you can see, it's not super clear, is where the has to do with the fact that the function, that the exponent operation is not commutative. It does not work the same forwards and backwards. That 2 to the third is different from 3 squared. 2 to the third is 8. 3 squared, on the other hand, is 9. So they're not commutative, and that's why these the symbols look similar, and students confuse them, but that's why they make different shapes, because the exponentiation is not commutative. It doesn't work the same forwards and backwards. Now let's look at the inverse. Again, I'm going to do the same thing I did. So my outputs are going to become my inputs. So when x is 1/8 and 1/4 and 1/2 and 1 and 2 and 4 and 8, those are going to be my x values. And then what were my inputs are going to become my outputs. So this was negative 3 for the input is now going to become an output of negative 3, negative 2, negative 1, 0, 1, 2, and 3. This is going to be a little harder to draw, but that's okay. So graphing this, starting with this first point, so that's going to be when the x value is 1/8, okay, and it's going to be down here at negative 3. It's going to be something like about there. When I got an x value of 1/4, it's going to be just a little bit more to the right, and my output is going to be negative 2. My for the next value at negative 1, it's going to be, or at 1/2, it's going to be negative 1, right about there. And then notice this, I've got this 1 and 0 here. When the x value is 1, it outputs a 0. That is the inverse of the exponential. When the exponent is 0, it has an output of 1. So that's going to go right here. When I have an input of 2 and it outputs 1, so it's going to go right there. When I have an input of 4, it's going to only output a 2, so that's going to go right here. And when I have an input of 8, it's going to have an output of 3. It's going to go right there. So what this graph looks like for a logarithm, it looks like this. That's what a logarithm graph looks like. Again, notice how it's it's flipped across the y equals x line. Okay, it's reflected across the y equals x line. So this is like the basic shape of a logarithm. You can sketch it out and see how that works. So let's notice some things. So what's the domain of 2 to the x? Well, it was all reals, but the range was from 0 to infinity. We did have a bit of a discussion about this is 0. And so, just like with the other inverses, what was the range is going to become the domain. So the domain is from 0 to infinity. And again, it's not a bracket. It never actually touches 0. And so there's actually a vertical asymptote here, just as there's actually a horizontal asymptote. It looks a little unusual because it's a one-sided asymptote. It really only affects sort of this part of the graph. It doesn't affect up here and doesn't have another side or anything. And then actually everything over here, if you were to plug in a negative value, you actually get an imaginary number. And then this actually becomes positive. So this the range is actually all reals for the logarithm, which is somewhat unusual. For 2 to the x, the left-in behavior had an asymptote at the 0. And for this one, the left-in behavior, there isn't any. Okay? Because it doesn't, I mean, technically it's imaginary, right? But there isn't. You know, does not, it's like a DNA kind of thing. All right, the right-in behavior for both of these is positive infinity. Infinities are hard to draw on this one. That was not bad. Also want you to notice both of these are increasing. The rate of increase of this one gets smaller and smaller. You'll learn more about that in calculus. and neither of them have maxes or have decreasings or mins. So that's what a logarithm looks like. Notice the difference between, and the key difference honestly between, yes, this looks like a square root function, okay? But the key difference is a square root function starts at the origin, a logarithm starts down here at negative infinity and goes through this point here. This is a crucial, if I were giving you a test, I better see the point 1, 0. The reason why I want you to see this point right there, or the equivalent, is that I want you to be able to like figure out if you ever have like a natural log. Let's say you forget what this is, you can go look on the graph, on your mental image of the graph, and remember, oh, right, that's 0. Okay? So that's another reason to, if you forget something on a test, you need to have these multiple connections so you can re-figure it out very, very quickly. So yeah, that's exponential and logarithms. That's what the function looks like. Looks what these functions look like and why they take the shapes that they do.